All right. Hi, everybody. Here I am with my dumb gamer headset to do the second half of this lecture. I'm in my dumb gamer headset so that I can speak to you most cleanly. It's my best mic. Yes, I don't know why this is the way it is. I hope you can all forgive me. All right, so let's go ahead and share the screen. Jump back into it. So I just reviewed the last video, and I believe that where we ended off was basically me covering k-means. So given that, what I'm going to do is I'm going to cover this, and then I'll do a quick virtual whiteboard example, and then we'll be good to go, I think. And then I am going to go ahead and I'm going to cover the assignment. In fact, I'm going to go ahead and do the helper video functionally. So the way the k-means works is that we're going to first initialize centroids randomly. The way that this works, right, is each of these centroids is going to be the center of a cluster. Now they're going to change a lot. The centers will change as the clusters will change. But the basic idea is that each centroid is going to correspond to a cluster, the middle of a cluster specifically. That's how we're going to define them. Then what we're going to do is we're going to have also a list of old centroids. We need that to be able to figure out if our centroids are still changing. That's the whole point. We're going to check and see while we're still changing, while our old centroids are not equal to our new centroids. We want to set our old centroids to our new centroids. Go ahead and calculate out our clusters, which is basically we're going to cluster or map or sort of connect each element to its closest centroid. And then finally, we're going to calculate some new centroids. This is what I was meant about the centroids changing, which is going to be the average of each cluster. And then finally, we'll return the centroids. So I think I can just click on this. Oh, cool. Oh, yeah. Thanks, Grammarly. So here's an example. So we have this set of data points, and then these clusters that just got created. So let me do this again, a little bit slower. So here are the data points. Those clusters got initialized. So we have this yellow, the blue. I'll try to move this bar a bit. The red and the green, right? And then from there, we map everything to each point, and each one of those update ticks is another iteration of this while loop. I'm about to show you an example that's much slower. But the final thing that we're going to get, right, is we're going to hit a point where the centers converge and are no longer changing. Right? That is the stable solution. Now, depending on the set of data points and the random initialization, we could get completely different final clusters. This generally means that we're going to rerun clustering many times and take sort of the best or the most consistent answer. So there's a whole bunch of examples there. We're not going to just keep watching that. So let me now swap over to a virtual whiteboard. So I'm going to stop sharing here, and then I'm going to go over here, and I'm going to start sharing here. Hey, it's me. But now I'm on a virtual whiteboard. Okay, so let's say that we have a space, right? Here's our space. And this is just defining, two variables. It doesn't matter what they are. We have some variable that's in our X and some variable that's in our Y axes. And let's say that we have a series of data points. Let's use a slightly different color. Let's say blue. I'm going to be consistent because in class I used a blue marker, so I'll be consistent. So then we're going to have a number of data points. Each one of these is a point of data, right? And if we're running clustering, the goal is to find what are the groups that are in this data. So what we're going to do is following that pseudocode, right? The first thing we need to do is init our centroids. So what I'm going to do is I'm going to initialize some centroids, some points at random. That'll be the centers of our clusters initially. Now, the important thing here is that this is called k-means. The reason why it's called k is because we have to give the number k of clusters that we're looking to find. So in this case, I'm going to assume that k equals 3. So let's go ahead and put 3 X's down. And I'm going to put these a little bit far away from each other. When they're randomly initialized, there's actually no guarantee that they're going to be sort of nicely spread out like this, but I'm cheating a little bit. So then once we have our initializer centroids, and while our centroids aren't changing, oh, sorry for my terrible handwriting. changing. Woo! All right. Then the first thing that we want to do, right, is we want to cluster, which again, what do we mean by clustering? What we mean is we're going to match each X to its closest centroid. So each of these blue X's to the closest red X. Now, this is going to require some eyeballing a bit because I'm not actually going to measure these things out. But assuming you're going to use straight line distance, Euclidean distance, I think it would look something like this. So we would have all of these clustered to this red X. We would have these clustered to this red X, and we would have these clustered to this red X. Okay. So that's that step. And the next thing we want to do is we want to recalculate our centroids. Because just eyeballing it, you should be able to see that several of these centroids should actually be in slightly different locations in terms of representing the average over these points. So I'm going to use a different color. I'll use yellow, and I'm going to go ahead and erase these lines because we're about to have brand new clusters. Oh, sorry, I shouldn't do that yet because we have to actually see where the cluster is. My apologies. Okay, so for this lower cluster, first of all, I think that the X, the midpoint, should probably be closer to over here on the left. There's 4 points on the left and only 2 points on the right. So I'm actually going to move it. Oh, hello. I'm going to move it right here. Okay, so that'll be our new centroid for that cluster. Then let's do it again for over here. Again, I'm going to move it a little bit over this way. And then finally, this one, I think is going to get probably pulled a little bit lower, given that there's 3 lower. So I think it's going to be about there. And then let's go ahead and erase the red lines. I'll keep the original centroids, the red X's, the first ones. But now we're going to iterate again, right? So after that, we're going to start our while loop again. Our first step is to cluster. So let's go ahead and again, match each blue X to its now closest yellow X, which are our new centroids. I could have used the same color. It doesn't matter. The color is not important. Don't fixate on the color. It's just the center of a cluster. So in this case, things are going to get shift a little bit. Are they? It's debatable. I'm going to shift things around a little bit just to force things to shift a little bit. This was a random initialization. It didn't have to work out this way. And let's do this. So this top left one is exactly the same. It hasn't changed which data points blue X's were in which cluster. But these 2 other ones are going to change pretty significantly, right? And so we could keep on going from there, right? Do I really only get these colors? What about colorblind people, huh? Anyway, from there, right, what we would do next is we would recalculate our centroids. So I'll use black X's this time. So in this case, I think that the black X would almost be exactly on this blue X. This yellow X, I think, should probably move even lower down. This yellow X is going to stay exactly where it is. Now, what's interesting, I'm going to go ahead and do one more iteration of this. Again, we're going to start the while loop again, which means that we are once again going to be on the cluster step. And that means that even though this X right here, the sort of black and yellow X that's like overlapping itself, that even though that didn't change, it's still going to end up picking up an extra point here just because of other centroids changing, right? We're going to get something like, I'm trying to eyeball distances. Is that closer? Is that closer? I'll do it like this. Okay. And it's going to change, but it will change less and less and less as we go along, and eventually we'll hit some equilibrium state. That's not guaranteed. You could iterate back and forth forever. So often you have like a little bit of a threshold for this line instead of just saying it's going to be while the centroids aren't changing anymore. We just have a little bit of a threshold, but that's the basic idea. Okay, so I'm going to go ahead and stop the share and restart the share on this side. Okay, so that's k-means, basic idea of k-means. Now, notably, I could have initialized those x's in different ways again, and it would have led to entirely different things. Also, we had to pick out k, right? We had to say how many clusters there were. We'll get to these issues in a minute. For now, we're going to get a different issue, which is there are going to be some situations where taking the mean of some data doesn't make sense. So, for example, if we had a collection of information on like I think I used the example of like children, like children's favorite animals, right? And one child's favorite animal was cow and one child's favorite animal was chicken. How can we take the average of a cow and chicken? Like maybe you could think of a made up animal for that, but that's not what we're trying to do here, right? What we're trying to do here is actually represent differences between things. So in those cases, it doesn't make sense to take the average over data points to find a new centroid. Instead, what we'll do is find the median of a cluster. So some of you might be saying, well, now hold on, how do you find the median when it's not numbers? Well, all this means is that it's the geometric median, which means it's the point closest to all other points in a cluster. That's what makes up the centroid. A couple things to note here. When we're initializing our centroids randomly, rather than producing fake new points, as with k-means, we're going to select a centroid from our data set, and that's going to be in our initial thing. And then when we're doing this here, again, our centroids are going to be a value in our data set. This is really helpful, right? One of the distinctions you can think of between k-means and k-metoids is that k-means is good in situations where it's okay to sort of approximate a fake data point. That would make sense. We're taking the average would make sense. And k-metoids really make sense in situations where it doesn't really make sense to approximate a fake data point. We don't want to say that this data point could exist, that this fake data point could exist. It doesn't make sense for it to. So in terms of determining k, which I mentioned is an issue, what we're going to use in this class is something called the elbow method, which is also what's used by data scientists. The basic idea here is that using some metric, we can approximate cluster quality. What we can do is we can run k-means many, many times for every value of k. And then we're going to plot out the average value of this metric across values of k. That's what this is over here. Don't worry about this metric. I'll get to what kinds of metrics we'll use in a second. But this represents like a k of 2, so 2 clusters, 2 centroids, a k of 4, 4 clusters, 4 centroids, etc. And you'll see something that looks like an elbow, right? It's the instance where we go from the most drastic change to next the least drastic change, or maximizing this equation. And this represents likely a good, the best sort of set of clusters according to this metric. In terms of metrics, you get things like average distortion. This is what you're going to be using for assignment 4. So the average distortion is the average distance between each member of a cluster and its center, right? The idea being that we want clusters that are close together, compact. Silhouette combines cohesion, compactness, with a notion that it should be also far away from other clusters, so you don't have like clusters overlapping. That's a separation. And then the Klinsky-Hurabaz index is similar to a silhouette, but it takes into account size and data set of k. You don't need to worry about these second two; they're just here as examples. This first one is really the one that I want you to know about. Okay, the other way that you can do this is with visual inspection. Sometimes it's really obvious, but not always. So in this sense, sure, we're in 2 dimensions and we can very clearly see that there's like 3 major clusters here. But what if we were in like 3 dimensions or 4 dimensions and we were only looking at 2 of them at a time? We wouldn't be able to tell if, even though it looks like there was 3 clusters, maybe 2 clusters were actually sort of like overlapping and they only became clear when you looked in that 3rd dimension. So this can be helpful to find sort of that you have to have at least this many clusters. You have to have at least this value of k, but it's not generally helpful for visual inspection to only use visual inspection to find your value of k. In fact, you shouldn't for the assignment. There's lots of other clustering techniques, but we're not going to cover them because this isn't a machine learning course. Plus, per this Quora answer, it isn't worth the trade-off, right? K-means is really good. K-means and k-metoids are really good, and they give good enough value that they're simple enough that it makes sense to just use those as opposed to all the engineering effort it would take for a more complicated solution. We didn't have time for this participation question in class, but I'm going to quickly go over it. So the idea would be to think of a game and a particular element of that game, like a player strategy, player deaths, that you could apply clustering to. Then I wanted you to think about, hey, what kind of distance function would make sense here? Because it's probably not just going to be Euclidean distance. It's probably not going to be Manhattan distance. It's probably going to be something that's domain dependent on what kinds of game and what kind of variables you're using in that game. And then finally, I wanted you to think about, well, how could these clusters benefit game dev? So what could you do with them? How could you use them to make the game better? My answer was to find the meta identification in Hearthstone using differences between decks. So counting the number of like edit distances to get between decks. This is actually just drawn from an example from a data scientist who was at Blizzard at the time, Alex Zook, which we're going to show in a future class, future lecture, apologies. So there's some pros and cons to clustering. One, or these k-metoids clustering. One is that we can learn this sort of big picture information, and it can help us cut down in complexity, right? The example that I gave in the other half of this lecture was that we could go from thousands of players to like 4 player types. And it can still give us a good answer, even with errors in our training data, because we can be robust to errors, right? So if we have one characteristic that is just like wildly incorrect, right? That's fine, because we're still going to say, hey, match you to the closest thing that we have. The cons, individuals can often get lost in the noise of the groups, right? We have no way of tracking individuals, basically. These decisions to open questions can hugely impact results. I'm going to get to open questions in a second. They're slow to build and even slower if we want to objectively decide on K. So it can take a long time to actually get the final cluster, not super, super long, but fairly long. You'll see as you're running it. But if we want to objectively find K with the elbow method, that means running a lot of tests, which you're going to have to do for assignment 4. It's also slow to use, but that's fine because this is offline, right? Clustering is not in the game. This is being used on game data outside the game by data scientists. So some open questions. One, how do we pick what variables to cluster on? So if we have lots and lots of variables, how do we know what makes sense? And then once we've made that decision, how do we know when to normalize or not to normalize, or to do something different than normalization? Because what we want, right, is to say, okay, these 2 variables, even if they have vastly different values, maybe one's in like hundreds and one's in like only tens of values, we want them to probably be equal in terms of their weight when we're doing a distance function. So how do we do that? How do we pick a distance function, right, outside of these things? And how do we use the clusters once we have them? Speaking of how we could use the clusters, one of the most commonly desired predictions that you might want to predict in games is churn. So churn is the rate at which customers are going to cut ties with a company. In games, what we mean is it's the rate at which players are going to stop playing a game. Players always stop playing a game eventually, but we want to minimize how quickly they do it. Churn is the most common problem player analytics teams are tasked with. Of how do you fight this? And on Wednesday, we'll talk about how you predict it. But let's go ahead and go over assignment 4. So, whoa, hello. Hello, Unity Hub. Go back to what I was trying to do. Oh my gosh, please, Unity, please let me open things. Okay. There we go. Okay. So for assignment 4, it's on clustering, unsurprisingly. So you're going to have to implement either k-means or k-metoids clustering. You're going to get something that looks like this. I think the easiest way to explain it is just by showing it to you. So every single one of you has your own unique data. And there's quite a bit of it, right? So if I open Matthew Guzdial's data, for example, we can see we're tracking a few things, right? For each user, we're tracking hours played, level, pellets eaten, et cetera. Basically, this is all synthetic data. It's synthetic so that I can guarantee certain things about it. I generated it. And it's basically synthetic data for this Pac-Man game we've been producing, right? Let's pretend we had, in this case, I forget how much data I produced, 1,000 players of your game, right? And this is all data from them. So what you want to do is go to main camera. And you'll see over here, data visualizer. What you want to do is click and drag train and verification into this slot for your data. You'll want to actually use different data. For example, the my data, because you know the K for that. You also are going to know the K for example and example 2 and all the TAs. So the 3 TAs also have their own data sets, and I've given you the K for those later on. But let's look at my data for now. And there's 8 variables, as I just showed you: hours played, level, pellets eaten, fruit eaten, ghosts, average, max, total, average score, max score, total score. And the idea here is that we can click on 2 of these variables and then visualize them, right? I could do level and pellets eaten. I could do pellets eaten and fruit eaten. Now, this is only 2 dimensions of the 8 dimensions of this data. If I do the same thing, it's going to be aligned because it's against itself, right? Pretty straightforward. But this allows you to get a rough sense of, well, hey, what's going on in this data. Now, notably, if I just look at hours played and level, you're probably going to go, 3 clusters, got it. Matthew's saying that you couldn't do this visually. what does he know? But if we go to the very bottom of this PDF, we can see is that actually there are 6 clusters in this data, right? So again, you cannot use visual inspection alone. Visual inspection is not going to do it. It's in bold right here. You're not going to be able to do it alone. You're going to have to use the elbow method. Notably, right, what was it? Gaussian average. Yeah, so I can see 1, 2, 3, 4, 5 sort of clusterish looking things here. But even then, right, I've got little bits coming off it. So there's indications here that it has to be above a certain value, but not at exact what value it is. And for that, you're going to need to use the elbow method. But let's talk this through in a little bit more detail. So again, this is going to be the stand-in for the helper video because, you know, 2 birds, 1 stone. So there's one script that you're going to be interacting with, and then another script. Technically 2, but one's just for holding data. And then one script is going to be for the extra credit. So the script for holding data is called data point. It's super simple. It's just holding data for you. Every user in your code is going to be represented by a data point. You're going to have the ability to get their score. You can do some other stuff, but it's just helpful for the extra credit. You really just need it to be able to like get information from it. That's it. Nothing complicated. K-cluster, on the other hand, is where you're going to implement your clustering algorithm, either k-means or k-metoids. It has to be one of those 2. And where you can, there's a few things that you're going to need to mess with. So K, right, is the number of clusters to create. You are responsible for setting this to the correct value. I'm not going to tell you the correct value. Figuring out the correct value of K for your specific data set is part of the assignment. Max attempts is going to be the maximum number of attempts to run the while loop. You can make use of it. You don't have to. Threshold is a way to determine how close the old pair of centroids and the new pair of centroids can be. It's a variable you can use, but you don't have to. There's a distance function. You are going to have to change this distance function. We'll get to why in just a second. Then we get to here. This is the basic cluster function. You are going to need to change this to implement k-means or k-metoids clustering. We'll talk about what it's doing right now in a second. And then finally, we have a few sort of helper things. We can calculate the difference between centers, right? This is just going to give you the minimum distance between the pairs of centers or centroids. Then you have a get median, which can pass in, you know, something representing a cluster, an array, of data points, and then get back a single data point is the median of that cluster. Use this for k-metoids, and then get average, which is used for k-means, right? Pretty straightforward. I'll get to the last thing, which is churn predictor. And in a second, I'll briefly touch on this as I usually do for briefly touching on extra credit, but I'm not going to touch on this in detail. So a few things. This is I've already covered up to step 3. So implement k-means or k-metoids clustering. Let's talk about that. So right now, if we look at k-cluster, we can see that what it's doing is it's using a k of 3, and then it is going to randomly select. This is the code to here. Let me pull this up. K-means. This is the code to randomly initialize. There we go. Initialize the centers. As you can see, sorry, I'm getting a call. If you can see from here, how this is doing it is randomly selecting a data point in the cluster. So technically, this is k-metoids, not k-means right now, because we could be on average, generating a point on average. Then we're going to instantiate clusters by these centers. The way that we're representing clusters is as a dictionary, where we have a dictionary going from the center of that cluster to a list of all the points in that cluster. If you're using k-metoids, make sure that you have you've included the center data point in this list as well. There's some special things that you're gonna have to pay attention to about that. I'm not gonna get into it. That's for you to find out. From there, what we wanna do is simply map each data point to the closest center. So that's all we're doing here. We're using the given distance function, which again, you're gonna have to change. And then we are, per here, changing out the dictionary, right? Setting that dictionary value. And that's it. You'll note I have included here the pseudocode for you. That's because here's sort of where you could do the pseudocode if you wanted to. And I've implemented old centroids as just an empty set. So let's go ahead and do a little bit more of this pseudocode. So while the difference between centers, old centroids to array is less than a threshold and the attempts are less than maximum attempts, what we want to do here is set our old centroids to centroids. Now, this is not exactly what you want to do because this is not going to exactly copy over a list. But if we look down here, what we can do is use toArray, and there is also a toList function. And there's also a copy function and a few different ways that you can do this. Anyway, so we could do, to ensure that it's not doing this sort of local copy, we could do toArray and then toList, which is pretty janky, but we can do that, right? And then you want to instantiate clusters by these centers, right? Which would be a case of reusing this code, but making sure that you're not just adding to these clusters by centers. Make sure that you are, in fact, reinitializing your centers entirely. So you use all this code right here. Instantiate clusters by these centers, and then map each data point. Oh, sorry, that's for the map each data point to its closest center. Instantiate clusters by these centers. This is the point where what you'd want to do is recalculate the centers. So this would be using either get median or get average to be able to do this line. So get median or get average per each center, right? You're gonna have to get a new centroid. Make sure that you've reinitialized centroids before you do this. So you do like, centroids equals new list data point like that, and then reinitialize your centroids according to each cluster. And then you'd want to map each data point to its closest center. And you can literally just use this code up above. Now, the distance function I mentioned, you're going to have to change. So let's quickly look at that. So distance function right now, if we go to the bottom, is looking at just the absolute difference between each thing to each other thing. Now, that's a problem because if we take a look at the data set, there we go. I don't need to see my to-do list. If we look at the data set, these values are wildly different from each other, right? Hours played versus level, there's like significant difference between these. So right now, hours played, the weight of hours played, if we just do like absolute value between these two points, the absolute difference between these 2 points, we're gonna get a significantly higher value than the absolute value between these 2 points. So we need to do something about that. You'll note that there's a whole bunch of values listed up here. Those are a hint. You're not going to be able to directly use these, but think about, hey, where could those values have come from? Note they're all the same for everybody. Think about that. You're going to have to make some changes. Okay, so the basic look of this is you are going to have to, if we jump back to the steps, you are going to have to finish creating this get clusters function. You're going to finish this, cluster, not get clusters. You're going to finish this cluster function, which basically looks like doing these things I just said, right? So using either get median or get median or get average here to initialize each of your new centroids, and then cluster each of them and changing your distance function. So once you've done that, fairly straightforward, pretty easy. Then once you want to do is you want to figure out your correct value of k. I'm going to tell you here, k can be only between 2 and 10 inclusively. You're going to have to probably use visual inspection and the ELBA method, as I just gave you, based on the average distortion. So the way that you can calculate the distortion is go into Unity, hit the play button. Again, oh, sorry. I left some bugs in my code. That's not good of me to do. Right. Are you happy now? Oh, right, because it wasn't actually called centroids. Geez. And it was instead called, what was it called? Centers. Okay, you happy now? Correct that too. Where are we at? Where are we at? Oh my God. I'm just going to go ahead and remove that. I'll just remove all of this because like that's going to go infinitely. Also, notably, the order in which you pass these two things into this function matters. I'm going to leave that to you to figure out. Trust you, because you can always just try the two variations that are possible to try. So again, what we're doing right now is we're just getting essentially 3 initial random clusters. So let's take a look at them. Right? It is it's based on the colors. So each color is a unique cluster in this case. If I hit distortion here, you can see down here at the bottom, it's printed out a distortion value, which in this case is very, very high because I haven't done anything to minimize this distance function. So once we've figured out the distance function, fixed the distance function, and figured out K, or not figured out K, finished our clustering approach, we then want to, for every value of K, try a number of times, calculate this distortion, figure out the average, create that plot like you just saw, or just maximize it with the function I gave you, find K according to this slide. That's that. And then optionally, what you can do is you can look at assign predicted churn. So again, I'm not going to give a lot of details here, but in train.cs, you can see that you have true, or some places there will be falses. These are whether or not that person churned. Right? So the idea is, and if you can see actually, here, I'll show you. Oh, sorry. What I want to do is this and this and this. Please hit visualize. Oh, sorry, I didn't hit the first one. If we pause here, we can actually take a look at them this way, and we can see if this check mark is blocked or is on, then it will have churned, and if not, they won't have churned. So the idea is that you'll be passed in for churn predictor. You're going to be passed in an array of verification data points, or in this case, it will be test data points, but you can test with your verification data points, and cluster by centers. This is going to be your clustered code, whatever you just clustered. And using that information, you can build something to predict what likelihood do we think it is that this set of data points that I first got passed, this verification data points, whether or not they are, whether or not they'll churn or not. That's it. So right now you can see that all it's doing is predicting true every single time. Hello? Okay, so if I hit calculate accuracy, oh, that's because I didn't actually return anything. Let's see, what did it get mad at me about? Because the dictionary. Oops. It's got mad, in fact, about churn predictor on line 10. Let's take a look at you. Line 10. Ah, yes. For a D, each data point and verification data points. Oh, am I not passing it in correctly? Oh, geez. Let's figure out what's happening here. Give me a second. I'm going to have to actually open this in MonoDevelop, even though I hate to. Let's see, where's this getting called from? Oh, just from data visualizer directly. Null reference. So it's somehow getting a null data point. Okay, well, let's just do this. D dot, if D not equal to null, just do that like this for now. Because maybe there's like an empty data point at the end or something. There we go. So if I calculate the accuracy, your default accuracy is going to be around 50%. But what we could do, for example, is, oh, I hecked up. I should have done this way. What we can do is we can use these various things. Like we could do like D dot, D dot level. That should be one. It's not just a system object. Oh, yeah, okay, yep. So that's just a level. Maybe we think anytime that they get above level 7, they're going to churn. And otherwise else, they're never going to churn. They love playing the game if they're before level 7. Level 7 sucks. We can go ahead and run that and calculate accuracy. And it's even worse. So you can use whatever you want to try to figure this out. You can look at the code yourself, right? You could You could use a decision tree, use some sort of learning method, right? Lots of things you could do here. The only thing you can't do is the only thing you can't do, apologies, I was dealing with something else. The only thing you can't do is use some external libraries. Also, notably, you're going to be using a test set. I'm going to be using a test set during the extra credit marking, auto grading. So you're not going to have access to. So you can't just, overfit to your training set or something like that. Okay. So in terms of the grading, the auto grading, the way that this is going to work is you're going to get 4 points for just a correct implementation of k-means or k-meta-weights. Very simple. Every point each cluster should be closest to its own center as opposed to another one. As long as you've implemented it correctly, you're good. That's easy. Everybody should get 4 points. Right now, right? The basic code given to you would get 4 points. You get an additional 4 points if your code correctly clusters each data point to the same hidden clusters, because when I generated them synthetically, I was generating them based on clusters. And that means that I know the true clusters, the true underlying clusters. Now, because this is a little bit random, I'll run it 10 times and I'll take the best. Finally, you need to identify the correct value of k. And I've given here exactly sort of how this grading will work. Finally, for extra credit, you get extra credit based on a test set you don't get to see. So if you get above 0.55, then you'll get 0.5 extra credit points. If you get above 0.75 test accuracy, then you'll get 1 full extra credit point. And otherwise, if you do even slightly better than random guess, 0.1 extra credit points. Or all guessing, all true or all false. Notably, the way you test this is with the verification set that I've given you. The verification set, the true answer, right? That's how you can do this calculate accuracy button. But the test set is withheld from you. A few hints to end us off. These are all the sets. If you look at the big set of data where I've given you the correct k value, you can use this to determine if all your other parts besides the extra credit have been implemented correctly. The distance function will need to change, as I've mentioned. Watch out for integer division. Don't divide by integers if you don't want some of your comparisons to be equal to 0. Don't try to do the guessing of k purely from visual inspection. You'll get it wrong. In 8 dimensions, you cannot tell through purely visual inspection. I've given you the elbow value of k. As I mentioned, you can click on the individual things to look at it. As I mentioned, you cannot set a list to another list in this way. It doesn't work like that. If you want, you can also change the cluster colors array. I'll show you that real quick. If you click on main camera, right, it's just this array right here. So if you don't like those colors, they're supposed to be colorblind friendly. I don't know. Then you can change them however you like. That doesn't impact anything, right? And then finally, for submission, all you need to do is submit kcluster.cs. And if you do the extra credit, churn predictor.cs. And that's it. Best of luck. As per the usual, check Discord and email for anything else. And I hope you have a good reading week because this will be due right after it. I hope most of you start well before then. Bye. And